We've noticed this year that most of the charts are from a Cessna aircraft. First question will be question number 16, 1016, and it might be advisable for you to get the chart out of the back of your book and follow us along. There's a lot of detail. It might not all show up on your television. Question 1016 on page 2 will refer to figure 1. What is the effect of a temperature increase from 25 degrees to 50 degrees Fahrenheit on the density altitude if the pressure altitude remains at 5,000 feet?
Well, Steve, first of all, we want to look at the chart and see what kind of information we'll get off the chart before we actually answer this question. And looking at the chart, we see that density altitude is along the left, outside air temperature is along the bottom, and we have pressure altitude off to the right part of the chart. They're saying what is the difference between a 25-degree temperature and a 50-degree Fahrenheit, 25 and 50 degree Fahrenheit, and you'll see that's on the bottom scale down here. Centigrade or Celsius is on the upper scale on the bottom of the chart. So we start at 25 degrees Fahrenheit and move up to the given 5,000 feet pressure altitude line, this slanted line here, and then move off to the left to find the density altitude at 25 degrees Fahrenheit and 5,000 feet pressure altitude. And we get something just under 3,900, about 3,850, let's call it. Then we look at 50 degrees and read up from the 50 degree Fahrenheit mark up to the 5,000 foot line again, and then over to our density altitude, and we'll get something over 5,000, looks like right at 5,500. So the difference between 5,500 and 3,860 is 1,650, and that would be the answer that we'd choose for this question, answer number 1, a 1,650 foot increase.
Question number 18. Determine the density altitude for the following conditions. We'll still refer to figure 1.
Okay, the conditions give us that it's, first of all, the altimeter setting is 2925. So now we're going to look off to the right part of this particular figure and find the altimeter setting versus pressure altitude columns. We find 2925, and I have it marked by a little arrow here. It's halfway in between 29.2 and 29.3. So we would take the average between the 673 and the 579, and the easy way of doing that is just adding these two together and dividing by 2, and when we do that we come up with 626. So we'd take 626 and add it to the airport elevation that we were given in our particular problem, and that was 5,250 feet. So 626 and 5,250 is 5,876. Now we're going to go into the left part of this chart with that 5,876 figure. They gave us that the outside, the temperature is 81 degrees Fahrenheit. So again, we start at the bottom of the chart at 81 Fahrenheit on the bottom, move up to a line that we mentally draw between the 5,000 and the 6,000 foot pressure altitude slanted lines here. 5,876 would be something close to 6,000 feet, and then we read from there off to the left to get our density altitude, and when we do that it's halfway between the 8 and the 9, or at 8,500 feet. So that's the answer to question 18, is answer number 3, 8,500 feet.
Okay, question 19. Determine the pressure altitude at an airport that is 3,563 feet MSL with an altimeter setting of 29.96.
Okay, for the two questions that we just covered, they asked for the density altitude, but now they're asking for the pressure altitude. So all we do is use the two columns on the right part of this chart. We find the 29, they give us the altimeter setting as 2976. It's going to be between the 2992 and the 3000, and actually it's halfway in between. There's no correction when the altimeter is 2992, and when it's 3,000, it's minus 73 feet, so halfway in between that would be minus 36.5 feet, or just rounded off to 36 feet. So we would subtract, since it's a minus figure here, we would subtract 36 feet from the given field elevation, which is 3,563 feet. We subtract 36 from that, we get 3,527 feet, and that's answer number 1.
Last question on the density altitude chart, question number 23. What is the effect of a temperature decrease and a pressure altitude increase on the density altitude from 90 degrees Fahrenheit and 1,250 feet pressure altitude to 60 degrees Fahrenheit and 1,750 feet pressure altitude?
Well, this is really a two-step problem. They give us two sets of conditions. One, that the temperature is 90 degrees and you're at a pressure altitude of 1250, and the second set of conditions is 60 degrees Fahrenheit and a pressure altitude of 1750. So let's go to, again, figure 1, and using the first set of conditions, 90 degrees Fahrenheit, we'd start at the bottom again, move up to the given pressure altitude of 1250, and it's going to be just over the 1,000 foot line, and here's the 2,000 foot line, so it's about a quarter of the way up from the 1,000 to the 2,000 foot line at this intersection, and then move over to read the density altitude under those conditions, and that would be 3,500 feet. Now the second set of conditions start with a temperature of 60 degrees Fahrenheit and a pressure altitude of 1,750. So again, it would be just below the 2,000 foot line, about 3/4 of the distance from the 1,000 to the 2,000 foot line, and then over to the left. And when we read that density altitude, that's 2,200 feet. So the difference between 2,200 feet and 3,500 feet is 1,300 feet, and it'd be a 1,300 foot decrease, because they're saying that we start at 90 degrees Fahrenheit and go to 60 degrees Fahrenheit. So we start at the 3,500 foot figure and go to the 2,200 foot figure, so it's a 1,300 foot decrease. Answer number 2.
Jeff, why don't you tell our students why they should be interested in density altitude and what this will do for them?
Well, as we spoke of in the curriculum under instruments and weather, I believe, we mentioned that density altitude and pressure altitude both change because of temperature and altitude, and these items you need to figure out the aircraft performance. In other words, as density altitude increases as you climb, you're going to have longer takeoff ground runs, we're going to have longer landing ground runs, and the airplane doesn't perform as well at higher altitudes and higher temperatures. Also, before we go on, I need to mention when we're doing all of these charts, they give you a plastic overlay to cover up the charts in the book, and they want you to use that plastic overlay so you don't leave your marks around to help out or to hinder the person taking the test after you.
That's what I was going to add too, is be wary of marks on the charts. You will see marks on the in the test booklet and on the charts, and often an examiner will just put them there and erase them and put wrong ones there to see if you're going to use that information. So figure them out on your own. They're not hard. Question number 26 speaks to what Jeff was just talking about concerning density altitude. Which combination of atmospheric conditions will reduce aircraft takeoff and climb performance?
It's answer 3, high temperature, high relative humidity, and high density altitude.
Question number 28. What effect does higher density altitude have on propeller efficiency?
It's answer 2, reduced efficiency because the propeller exerts less force than at a lower density altitude.
Okay, now we'll jump over to page 26, question number 331. What is the headwind component for a landing on runway 18 if the tower reports the wind is 220 degrees at 30 knots? We'll refer to figure 24.
Go ahead and get figure 24 out, or at least turn to it in your book, because it is a rather complicated chart from the standpoint of the lines are hard to read, especially on the television. So I think you'd do better if you had it right in front of you as we referred to it. Figure 24 is a crosswind and headwind component table. In other words, you can read the headwind on the left and the crosswind on the right from a given wind. Now, our problem gives us that the wind is reported at 220 degrees at 30 knots. Now, if it's a tower reported wind, that's magnetic. Runway is 18 or 180, that's magnetic. So you just subtract 180 degrees from 220 degrees to get 40 degrees, and that would be the first figure that we would enter this chart with, the 40-degree figure. The 40-degree line, then you come down that line until you intersect with the 30-knot curved line, and that would be right here, 30-knot curved line. And then they're asking what is the headwind component. So you would read straight across to get the headwind. If they ask for the crosswind component, you would read straight down to read the crosswind. But reading straight across to get the headwind, there's 20 knots. This line is 25, and then there's 30 knots. So we're reading something less than 25 knots right at 23 knots. And so that would be answer number 2, 23 knots.
Question number 332, next question, same chart. Determine the maximum wind velocity for a 45-degree crosswind if the maximum crosswind component for the airplane is 25 knots.
We would use this same figure, figure 24, but in a slightly different way now to answer this question. They give us that the maximum, it's a 45-degree crosswind, and the maximum component for the airplane, which you would get out of the operator's manual, is 25 knots. So we would enter at 45-degree line, and here's the 40-degree line, 45-degree line, so the 40 and 50, so the 45-degree line is right in between. And then we would also start at the crosswind component line at 25 knots, which is given, and when we would read up until it intersected this 45-degree line, and then that intersection will give us the maximum wind component, or maximum wind velocity. This is the 30-knot curved line. This is the 40-knot curved line, so this is just about halfway in between the 30 and the 40, right at 35 knots. So it's answer number 4, 35 knots.
One more question on this chart, question 333. With a reported wind of north at 20 knots, which runway, we have a choice of 6, 14, 24, or 32, is appropriate for an airplane with a 13-knot maximum crosswind component?
Well, we can look at each one of those crosswind components of the 4 choices, but let's rule out 2 anyway. First of all, they tell us that the winds are from the north, through 360 or 000, and that if it's a north wind at 20 knots, certainly you're not going to be taking off to the south, whether it's the southeast or the southwest. So we can cross off or throw out answers number 2 and 3, runways 14 and 24, because you wouldn't be using those with the wind from the north at 20 knots. So it's either going to be answer 1, runway 6, or answer 4, runway 32. Runway 32 is 40 degrees off the wind, given the winds are from the north, and runway 6 is 60 degrees off the wind. So let's just look at runway 32 first, since that's closest to the wind, and that'll probably be the right answer. Now they give us that it's 13-knot maximum crosswind component, and if we're using runway 32, remember that's 40 degrees off from the given wind if the wind is at 360 or out of the north. So again, we would start at the 40-degree line and read down and intersect a line coming up from, or actually we're given that it's 40 degrees at 20 knots. So the 20-knot wind would be this curved line, the intersection of this 40-degree line and the 20-knot line, and then read down to the crosswind, and that's right at 13 knots, just a little bit under 13 knots. So runway 32 would be acceptable under these conditions. So the answer to question 1333 is number 4, runway 32.
Thanks, Jeff. Now we'll go to another chart, figure 25, and work a fuel consumption problem. This is a real-life problem. Crosswind component charts are a real live problem for a student pilot, because as you know, you have a crosswind limitation that your instructor puts on you for solo.
I might say the crosswind components, I use this particular chart, I call it a spider web chart. It obviously looks a little bit like a spider web. I use that chart in my flying every day. Maybe not every day if the winds are light, but anytime there's a problem with tailwinds or crosswinds, I get that out all the time. So it's something you're going to be using for probably the rest of your flying career.
Are you saying you have a crosswind limitation in the big jet you fly?
We do have a crosswind limitation, that's correct, but most often it's in tailwind. So I try to figure out what kind of tailwind we actually have to figure out. Then I go into my performance charts, which list tailwinds, and see if I can take off on a certain runway. And sometimes I can't. We have to taxi against traffic. Maybe we're heavier than everybody else compared to our maximum allowable takeoff weight, so we have to only have a headwind. That's happened more than once, especially here at Denver when you have high density altitudes.
Flying light planes, really, once you have experience and can handle the plane, you're only limited by the amount of total control deflection against the wind, and the fact that once the plane's sitting on the ground, that the wind won't actually just blow it over. Right. So it's pilot technique has a lot to do with it. Okay, let's go to figure 25, question 337, and work a fuel consumption problem. What is expected fuel consumption for a 1,000 nautical mile flight under the following conditions? We see that pressure altitude is 8,000 feet, temperature is minus 19 degrees Celsius, manifold pressure is 19.5 inches of mercury, and the wind is calm.
Well, first of all, let's look at figure 25 and see what kind of information that it gives us. First of all, it is a cruise power setting chart, and there are 3 basic groups of columns. We have ISA minus 20. ISA is International Standard Atmosphere. We're saying that's 20 degrees colder than standard for this area. We have a standard day for this area, and then off to the right we have ISA plus 20. So we're going to have to find, first of all, where we are in the temperature realm, if you will, under these particular conditions. Now they give us that the temperature is minus 19 degrees Celsius. So we need to figure out the standard conditions, what the temperature should be at 8,000 feet. Now to figure out the standard temperature at a certain altitude, remember we double the altitude, subtract 15, and then change the sign. So we double the altitude of 8,000 feet, that's 16, subtract 15, that's 1, change the sign is minus 1, so standard conditions, standard day, would be minus 1 degrees Celsius at 8,000 feet. Well, we're given that the temperature is minus 19 degrees Celsius, so we're actually 18 degrees colder than standard. That's very close to our 20-degree figure on the far left-hand column, so that's the columns that we'll be using. We'll be using the ISA minus 20 section because of the conditions given. Now they're saying we're at 8,000 feet, and so we can read across at 8,000 feet for the true airspeed in knots of 157. So we're given that or we find that we have 157 knots true airspeed. Now we're given that there is no wind, the winds are calm. So true airspeed equals ground speed when the winds are calm. So that would be our ground speed, 157 knots. We're given that we want to go 1,000 nautical miles, so we would divide 1,000 nautical miles, which is given in the problem, by 157 knots, which is our ground speed, to get the number of hours that it would take us to go 1,000 miles at a speed of 157 knots. And when you do the math, divide 1,000 by 157, we come up with 6.37 hours. 6.37 hours then would be how long it would take us to go 1,000 miles at 157 knots. Now I go back into the chart to see what kind of fuel flow we have under these particular conditions. We find that at 8,000 feet again, our fuel flow is at 11.5. So that's 11.5 GPH, gallons per hour. 11.5 gallons per hour, and we know we came up with 6.37 hours, so we just multiply 11.5 times 6.37 to get our total fuel consumption for this particular flight, and that would be 73.25 gallons. That's closest to answer number 4, 73.2 gallons. I might mention, when you do all this math, very often you'll be a little bit off from one of the answers. Like in this case, we came up with 73.25, and the closest choice was 73.2. Just choose the closest choice. Their math, they may round off before you round off, or you may round off before they do. Choose the closest choice of the 4 answers given, and you'll most often, you will be correct.
Mm-hmm. Question 339. What fuel flow should a pilot expect at 11,000 feet on a standard day with a 65% maximum continuous power?
Okay, we're given in this problem that it's a standard day, so we can look under the columns under standard conditions or standard day to find the data that we're going to have to find. Now they give us that we're at 11,000 feet. We look under the standard day columns. There is no 11,000 foot row. There's a 12,000 foot row and a 10,000 foot row. 10,000 feet, the fuel flow in gallons per hour is 11.5. And at 12,000 feet, the fuel flow in gallons per hour is 10.9. So we would just add those two numbers together and divide by 2 to get our answer for 11,000 feet, which is halfway in between the two. And when we do that, we come up with 11.2. That's answer number 2, 11.2. Let's move on to page 28, question 351. We'll look at figure 28. It's a landing distance chart. Got it? Okay, question 351. Determine the total distance to land the airplane under the following conditions. OAT, or outside air temperature, is 32 degrees Fahrenheit. Pressure altitude is 8,000 feet. Weight is 2,600 pounds. We have a headwind component of 20 knots, and we have a 50-foot obstacle at the end of the runway. This chart is a rather complicated looking chart, and it's very easy to get lost in this chart, especially since we have a plastic overlay between us. I would suggest when you walk in to take this exam that you bring a straight pin, something that won't leave a mark on the
pin.
A straight pin, yes. A hat pin or a sewing pin, something like that. Something that won't mark the chart, and you can get very accurate because it's sharp, and then you can trace your movements that we're going to show you that you need to do on the chart without the plastic overlay, because as soon as you start doing on the plastic overlay, the overlay is going to shift and you're going to get lost. So use the pin, and that'll be a lot easier.
Well, what we're saying is you're more interested in your test score than the next guy's test score, and you're going to want to get in on these charts as close as you can.
So let's look at the chart. The chart basically gives us a landing distance, and you can see that there's a dark black line right here, and that follows an example problem in the upper right. So if you absolutely forget how to use this chart, just look at the example and kind of trace through the lines that they've already drawn, and that will show you really how to use this chart.
What you're saying is you don't need any knowledge as long as you follow the example.
That's correct, because they give you example conditions and an example method of finding the answer, and so really you can just walk in never having seen this chart before and do it, as long as you're accurate using some sort of a sharp object. So let's use the conditions that they actually gave us. They gave us that the temperature was 32 degrees Fahrenheit and that the pressure altitude is 8,000 feet. We would start down in the lower left-hand corner then of the chart where it says outside air temperature. The lower numbers are in Fahrenheit, shown here, and the upper numbers are in Celsius, shown here. So we want to use the Fahrenheit numbers, and 32 degrees, of course, is the same as 0 degrees Celsius. So we would start there and move up to the slanted line that is labeled 8,000 feet. And you can see that these lines are pretty close together, so that's why we have to be pretty accurate in tracing through this chart. Once we have an intersection on this type of chart, we move parallel straight over to a reference line. So we go over to the first reference line straight from the intersection of 32 degrees and 8,000 feet over to the reference line. Once we reach that reference line, now we're going to correct for weight. And they give us that the weight in this particular problem is 2,600 pounds. So we would follow these guidelines, these three slanted lines or guidelines. We would follow parallel to the guidelines until we intersected with the 2,600-foot line coming up here. When we do that, we come up with another intersection. Once we find an intersection of two conditions, we move over to the next reference line. So we're on the second reference line, and now we need to correct for wind. Now they give us that the wind, headwind component anyway, is 20 knots. Notice that you have some solid lines slanting down to the right, and you have some dashed lines slanting up to the right. The solid lines slanting down are headwind. The dashed lines slanting up are tailwind, as labeled right here on the chart. So just be sure you follow the conditions given. They give us that we have a 20-knot headwind, so we would follow these guidelines, the solid guidelines going down to the right until we intersect with the 20-knot line coming straight up. Once we have our intersection again, we move straight over to the next reference line, and either we're going to correct for an obstacle or it would be 0, in other words, no obstacle. If it had no obstacle, you'd read straight across through that reference line. But in this condition, we're given that we have a 50-foot obstacle, so we read now parallel again with these slanting guidelines up and to the right, following these guidelines until we reach the 50-foot line coming up from the bottom, and then we read the final number, which is distance in feet, off the right. Now here's 1,000 feet, here's 1,500 feet. Each one little tick coming off the side then is 100 feet, and we're right at the one tick below 1,500 feet or 1,400 feet. That's answer number 2, 1,400 feet.
I'd like to mention that you can be sure the alternate answers in these performance charts are accurate, that you'll come up with these alternate answers if you make one wrong move at a reference line or go in the wrong direction. So really do them carefully. Really, this particular chart is an exercise in you following instructions, since the sample on the top of the chart is there and shows you how to do it. And you want to get comfortable with these because you're going to be using them all the time, especially for certification in your early years of flying. As you get a little more experienced in flying, you get a better handle of the performance of the planes you fly, and you might not go in these unless there's a real question about performance capabilities and whether you're going to be able to get on or off a
Remember,
runway.
you're always responsible for the performance
Determine
determining
runway,
the runway
FAR
length.
91.5.
Right. So you're always responsible for determining it. Now, if you're flying at the same airport, the same conditions, and the same weight for 2 or 3 weeks, you can say, well, I did it last week or yesterday or whatever. But until you're absolutely sure that you're within limits and all of that, always pull out the charts, even for just a local training flight.
Question number 356, we're going to look at a landing distance chart, another type of chart. It's figure 29. It's right below the one we just covered. What is the total landing distance required to clear a 50-foot obstacle with the following conditions using the landing distance chart?
Okay, notice on the landing distance chart, you have a couple of broad categories at the top here. You have at sea level, you have at 2,500 feet, 5,000 feet, and then 7,500 feet. So you have 4 basic elevations, and you'll find that all of these problems will start us out at one of those 4. Now we're given that we're at 7,500 feet pressure altitude, so we'd start off to the right, and the headwind is 8 knots. Well, first of all, they can ask for one of 2 things. They can ask for the ground roll or the total distance to clear a 50-foot obstacle. Under each one of these elevations, you have different numbers for ground roll and the total to clear a 50-foot obstacle. So be sure you're looking at the numbers that they are referring to, and in this case, they're referring to the total landing distance required to clear a 50-foot obstacle. So it would be the column off to the right under the 7,500-foot area, and that number is 1255. Now, we need to correct for some numbers given in the problem, and to do that, we look down at the notes. The notes, first of all, say decrease the distance shown by 10% for each 4 knots of headwind, increase the distance by 10% for each 60 degrees Fahrenheit temperature increase above standard, and then number 3, for operations on a dry grass runway, increase distances, both ground roll and the total to clear 50-foot obstacle by 20% of the total to clear 50-foot obstacle figure. Okay, so they give us that our headwind is 8 knots. We look at note 1, where it says decrease the distance shown by 10% for each 4 knots. Well, if we're given that we have 8 knots of wind, that's double 4 knots, obviously, so it's double 10% or 20%. So we would subtract 20% from the figure that we came up with, which was 1255. When you take 20% from 1255 to do electronic calculator is very easy. You just subtract the 20% figure on your keys. By the way, you can bring an electronic calculator in, and we recommend you do so. If you have to do it manually, just multiply times 0.2, that's 20%. Take that figure and subtract it from 1255. Either way, you'd come up with 1,004, but that's not the final step, because they give us one more thing. They say the runway, first of all, they say the temperature is standard, so we don't have to correct for temperature, or note 2, but we do have to correct for note 3, which is a grass runway. That's what they give us in the problem. And it said that we would increase the distance by 20% of the total to clear 50-foot obstacle. So we take that 1,004 figure, which is corrected for headwind, and increase by 20% because it's a grass runway. And when you take 20% of 1,004 and add it to 1,004, that's 1,205, 1,205 feet, and that's answer number 2.
Okay, the next question deals with the same chart but asks a different problem. Question 357, determine the approximate landing ground roll distance from the landing distance chart, which brings up a point that you should read the questions carefully and decide what they're asking, even in the performance section.
That's correct. It's very important. I think probably more important to be nitpicky when you're reading these questions in the performance section, and weight and balance, because there are perhaps 2 or 3 different things that they could ask you from a particular chart. So be sure you're aiming for what they're asking. Apples and apples and oranges and oranges. Looking back at the figure 29, they give us that the altitude is 3,750. Well, we have a 2,500 foot column and a 5,000 foot column. So we're going to have to interpolate. Now, the ground roll, which is what they're asking for 2,500 feet, is 470 feet. And the ground roll under 5,000 feet is 495 feet. 3,750 is exactly halfway in between 2,500 feet and 5,000 feet. So we would just interpolate, or take the average between the two. We'd add 470 and 495. divide by 2, and we come up with 482. So 482 then would be somewhere in between, or exactly halfway in between at 3750. But we need to correct for wind. They say the headwind now is 12 knots. Again, we go to note 1, and it says decrease by 10% for each 4 knots. So 12 knots is 3 times 4, so we would decrease it by 30%, or 3 times 10%. We take that 482, subtract 30% from it, we come up with 337.4, and the closest answer that they have is answer number 2, 338.
Jeff sure has a way of making math look easy. He's an engineer. He's taught flight engineer schools for us for the last 10 years, and a lot of people don't like math, Jeff.
Well, that's true. A lot of people have a problem with math, and I understand that. That's why I'm trying to say that these problems are basically easy. When we get into ATP and flight engineer, the math sometimes gets a little complicated. But in the private, we're talking basic averages, adding 2 numbers and dividing by 2, or taking 20% of something, or 30% of something. So really, the math necessary is pretty easy in the private. I'm trying to show you in a basic, straightforward way how to do it. And it really helps, again, if you've got a calculator.
And practice makes perfect. In your sample exams, you'll have a chance to work all these questions we're not covering. We're just doing representative ones to show you how to get into the charts. We've got one more, question number 367 over on page 29. We've looked at crosswinds, we've looked at density altitude, we've looked at landing, and we haven't looked at takeoff, and this is a takeoff chart. 367 refers to figure 31. Determine the total distance for a takeoff to clear a 50-foot obstacle. It says the outside air temperature is standard. Pressure altitude is 4,000 feet. Our takeoff weight is 2,800 pounds. And we have a headwind component, which is not a component, is calm.
Let's look at that chart, which is a takeoff distance chart, figure number 31. Again, just like the landing distance chart, it has an example in the upper right-hand corner, and it has dark lines which give you the answers, or how to determine the answer for the example. So again, if you had never seen this chart before, you could look at the example, follow through with these dark lines which show you how they figured out the answer, and it also gives the answer. So just like I said on the landing distance chart. Now they give us that the temperature is standard, outside air temperature is standard, and pressure altitude is 4,000 feet. Well, rather than figuring up standard, they also have an additional line right here, which is kind of this curved line going down to the right, labeled ISA. Again, ISA is International Standard Atmosphere, and that's just saying that is the standard temperature at each one of these altitudes, pressure altitudes. So all you have to do is find the intersection of the 2 numbers, which are the 2 lines, the ISA line and the 4,000-foot pressure altitude line, which is given in the problem, and the intersection is right here. So that's where we'd start. We would start at that intersection rather than starting down at a temperature. Once we have an intersection, like the landing distance chart, we move over to a reference line. Here's the reference line, and now we correct for weight. Now they give us that the weight of the airplane is 2,800 feet. 2,800 is just to the right, so again we follow parallel down with these guidelines from the reference line, so we go down parallel to them until we intersect 2,800 foot line, which comes up, 2,800 pound line, which comes up. Once we have an intersection, then we move over to the next reference line. We're on the second reference line, and now we need to correct for wind component. Well, they say the winds are calm, so there is no correction. Remember, tailwind is the dotted lines going up. Headwind are the straight lines, solid lines going down to the right. So be sure if there is a wind, you use the correct guideline as your guide. Since there is no correction, we stay on this same line moving off to the next, over to the right to the next reference line, and now we need to correct again for an obstacle, and they give us in the problem that it's a 50-foot obstacle, so we move up parallel to these guidelines on the right until we find the intersection with the final line off to the right, and it's somewhere between, here's 1,000, here's 2,000, this would be 1,500 feet, so something above 1,500 feet, and if you do this accurately again with your straight pin, you're going to come up with 1,750, and that's answer number 3.
That wraps it up for performance charts. Good chance you'll get asked 1 question off each chart, 3 or 4 questions for this section. I've taught hundreds, thousands of student pilots, and a lot of people are intimidated by this. You've been out of college a long time, you never went to college, you haven't had to work with stuff like this. Just take your time, watch the tape again, work the sample problems. This shouldn't give you any trouble.
In this navigation section, it's really going to be almost the final exam. We're going to use information from the AIM sections, from the FARs, airspace, and really just use the questions as our vehicle to discuss the different things involved with navigation. So why don't we start with the question
Okay.
to start off with.
Page 16, question 197. What is the recommended procedure for a flight from Jamestown VOR DME northbound on Victor 170 through Devils Lake East MOA, or Military Operations Area, when the MOA is activated? We'll refer to figure 13.
Well, figure 13 is one of the colored charts in the book that come in the questions. And the Devils Lake MOA, or Military Operations Area, is shown up here in the left-hand side. Just to give you an idea of how it's shown, it's got a little checkered, if you will, border down here, and that's how the MOA is actually shown on the chart. And the answer would be to number 2, contact the Jamestown Flight Service Station for traffic advisories. Let's move down to Jamestown. We can see Jamestown Flight Service Station says FSS, so that's how we'd know we would talk to Jamestown Flight Service Station, and we'd get traffic advisories on the MOA telling us whether or not the MOA was active, in other words, it was being used, or if it was, and they sometimes call that hot, and if it was cold, meaning it's not in use.
Question 198. The Common Traffic Advisory Frequencies, or the CTAF, for the FSS at Jamestown Airport, Area D is?
Again, figure 13. Area D is down the lower left-hand corner showing Jamestown area, and in the numbers for Jamestown we have on the very right 123.0, and that's the CTAF frequency, so it's answer 3, 123.0.
Question 199. What is the recommended communication procedure when inbound to land at McVille Airport, Area A?
Well, Area A on the chart's way at the upper right-hand corner of figure 13. McVille Airport does not have that frequency number at the end of it. It's blank. So in that case, we use multicom frequency, which is 122.9. That's answer number 1. Broadcast intentions when 10 miles out on 122.9.
Question 201. What is the recommended procedure for contacting FlightWatch in the area depicted by figure 13 for the en route flight advisory service?
Well, what you do is you look at figure 13 looking for a box that says FlightWatch in it, and it's about in the center, lower center, right above the letter E in figure 13, where it says Grand Forks FlightWatch. And so we would talk to Grand Forks FlightWatch, and any FlightWatch, or EFIS, is found on 122.0, or uses frequency 122.0. So it's answer number 2, contact Grand Forks FlightWatch on 122.0.
Question 217 presents a problem with longitude and latitude. You're not going to run into this in your aviation until you use LORAN, area navigation, or the new GPS system, the satellite system, which isn't in effect yet for general aviation. Question 217, what is the approximate latitude and longitude of Cooperstown Airport?
Well, before we get into answering that question, let's talk about latitude and longitude just a little bit more, Steve. Latitude and longitude are based on lines drawn on the globe, and they start at Greenwich, England. That's our prime meridian, and they start at the equator. So if we're talking about west latitude, that's west longitude, I mean, that's the number of degrees west of Greenwich, the prime meridian. East would be east of the prime meridian. And then when we have north or south, that of course would be latitude, and that's north or south of the equator. 10 degrees north is 10 degrees north of the equator. 90 degrees north is the North Pole. So that's how latitude and longitude are shown on the maps. And like Steve said, you're probably not going to ever use them as a private pilot unless you do have LORAN or Omega or some other rather involved navigation system. So to answer our question, first of all, we're talking about Cooperstown Airport, just above Area B in figure 13. Cooperstown Airport, what we need to do is look around this figure 13 to find where our lines of latitude and longitude are drawn. Well, down here in the lower right-hand corner, we have a line that goes horizontally, and that, of course, would be north latitude, labeled 47 degrees. So there is 47 degrees north. There's also a vertical line right here labeled 98 degrees, and that is west longitude. So at the intersection of these two lines would be 98 degrees west and 48 degrees north. So now we have to find where Cooperstown Airport is in reference to that. Well, if we drop down Cooperstown Airport to our 47 degrees line here, there are little marks along the line giving us each one is, well, you break down, by the way, degrees, minutes, and seconds. So each one of those would be 1 minute. So we would go from 98 degrees west. You find that if you drop down Cooperstown Airport, it comes out to right at 6. So that's be 98 degrees and 6 minutes west longitude would be the for Cooperstown. Now we have to find out the latitude. So we'd come up now above Cooperstown. We see a line above Cooperstown. That is 4730 or 47.5 degrees. So between 47 and 4730, you count down again. Each one is 1. That's 4725 north. So the answer would be 4725 north latitude and 9806 west longitude. And that's answer number 1.
Yeah, they've got an answer waiting for you if you make a mistake number 2. If you accidentally interpret that line Jeff referred to as 47.5 or 47 degrees 30 minutes, they've got an answer waiting for you at 47.55, which would be wrong. So watch that carefully if you get asked this on the test. Next question is 222 on page 18. What hazards to aircraft may exist in areas like the Devil's Lake East MOA?
Well, we've already referred to the MOA on the chart, and again, it's in the upper right-hand or upper left-hand corner of chart 13. But any MOA or military operations area just tells you that there's extensive military traffic and most likely training traffic involved within that area. So it's answer 2, high-density military training activities.
Question 223. The airspace overlying and within 5 statute miles of Barnes County Airport, Area F, is?
Area F is down in the lower right-hand corner. We find Barnes in this magenta circle right here, and the label Barnes shows us that that's what we're talking about. Notice that we have kind of a purplish-brown shading. That is called magenta. Anytime you have that purplish-brown shading, controlled surface, or the control zone, if you will, not the control zone, but controlled airspace, starts at 700 feet above the surface. Now notice right above that we have kind of a blue shading. That's 1,200 feet. So anytime you have this blue shading, that's the control surface or control area starts at 1,200 feet above the surface. Anytime you have the magenta shading that starts the control surface, controlled area, again I mix that up, starts at 700 feet. Now notice right over here that it's a sharp line. It's shaded out blue to the left, but to the right it's just a sharp line. Well, this area right here is uncontrolled airspace up to the base of the Continental Control Area, which is 14,500 feet. We'll be talking about that to answer another question. To go back to the question they asked, then, we're talking about uncontrolled airspace from the surface to 700 feet and then controlled airspace 700 and above. So it's answer number 3, uncontrolled airspace from the surface to 700 feet, AGL, above ground level. 224.
Question 224. Identify the airspace over Farm Airport that exists from the surface to 14,500 feet.
Hogarth Farm is to the left of marker C, and you notice that it's within the area that has that straight line. Remember, the shading goes in this direction, so the controlled airspace starts at 1,200 feet on this side of the line, but the controlled airspace starts at 14,000 feet, 14,500 feet on this side of the line. So it's uncontrolled airspace above this, private airport here from the surface to 14,500 feet. And that's answer number 1, uncontrolled airspace, surface to 14,500.
So my only comment is big deal. I mean, so what does all this mean to us? What it means at that little airport, when we're talking about control here, we're not talking about air traffic control, we're not talking about your radio, we're not talking about you being controlled, we're talking about weather minimums, and that's what control is all about. Control area, control zone, continental control area. when we use the word control, we're talking about controlling you guys to stay away from these guys with marginal weather. So that airport he just pointed out, which is on the other side of the hard blue line, means that if the controlled airspace doesn't begin until 14,500 feet MSL, we need to use the cloud and visibility requirements for uncontrolled airspace, which means not much is required. So that's what we mean when we're talking about control. It's the most confused and misunderstood statement in pilot training. Question number 225. The visibility and cloud clearance requirements to operate VFR over Cooperstown Airport, Area B, between 1,200 feet AGL and 10,000 feet MSL are...
Well, Cooperstown Airport, remember, we already found that to answer our latitude and longitude problem. It's just above marker B, and it's within this uncontrolled airspace line. We're on the hard side of this line. So they're telling us that we're in uncontrolled airspace, and also we're between 12,500 and 10,000 feet MSL, between 1,200 feet AGL and 10,000 MSL. So an uncontrolled airspace between above 12,000 AGL and under 10,000 feet MSL. It's answer number 2. 1 statute mile visibility, 1,000 above, 500 foot below, and 2,000 feet horizontally from clouds.
You can see that that cloud chart that I covered under regulations is pretty important. It's so important that one of the first things you might want to do, and I just say might, it depends on your own style, when you go into the exam room, is to sit down and write out that cloud chart for controlled and uncontrolled airspace before you even start the exam, because you're going to get a couple questions, either under regulations or in here, dealing with cloud and visibility requirements. Our next question is number 226 at the top of page 18. The minimum altitude to be maintained above the Arrowwood National Wildlife Refuge is... You don't even need to look at the chart to answer the question.
That's true. You don't need to look at the chart, but let's look at the chart just to show you how the chart would give you this information or what you would see. And this is to the left of Arrow C or Area C. You see some little writing there. It says Arrowwood National Wildlife Refuge, and that's all you're going to see on your sectionals. So remember when Steve was talking in the FAR section about that, you want to maintain a minimum of 2,000 feet above. That's 2,000 feet AGL. So it's answer number 3, 2,000 feet AGL.
You know, we believe in giving you as many free points as you can to pass the test. If it was up to me, I'd give you 50 free points and give you 100 as long as you knew how to fly. In Appendix 2 on page 1 is a legend for a sectional chart. And you'll get free answers here if you need them. So anytime you're in doubt about something on the sectional chart, and there'll be things we'll refer to, you can find it by looking on the legend on Appendix 2. A lot of the FAA's philosophy in giving this test is it's a minimum. They're testing for your minimum ability, not your maximum ability. One thing they want to know is that you're critical and that you know how to look things up, that you don't have to have the answer for anything as long as you know where to go for it. Next question is number 227. What hazards to aircraft may exist in warning areas such as warning W50 in Figure 14?
Well, let's look at Figure 14 and see how a warning area is depicted. And a warning area, remember, is just like a restricted area, but it's in international airspace, or it's outside of the 3-mile limit over international waters. And it's just shown by a W50. And anytime you have a warning area, just like anytime you have a restricted area, there may be hazards to flying or hazards to aircraft within that area. So the answer is number 1, unusual, often invisible hazards such as aerial gunnery or guided missiles.
Thanks, Jeff. 228. What minimum radio equipment is required to land and take off at Norfolk International, Area A?
Let's find Norfolk International on Figure 14, and it's near Area A. And you'll see, first of all, that a VOR box saying that it is Norfolk, but Norfolk Airport is this blue airport diagram right here. And anytime you have a blue airport diagram, you know that you have an airport traffic area. In other words, you have tower, you have communications procedures, and anytime the tower is operating, you must have an operating radio to be within the airport traffic area, 5 statute miles from the center of the airport up to, but not including 3,000 feet above ground level. So it's answer number 1, a VHF transmitter and receiver.
Next question is 229. What type military flight operations should a pilot expect on IR-644?
Let's look at Figure 15 and find IR-644 just to see how it's depicted on a sectional. It's this dark or light gray line, and there's you can't see it too well, but it says IR-644 right here. And all that is a training flight for military aircraft, or I should say a training route for military aircraft, and an IR route is above 1,500 feet AGL or above ground level. So it's answer 4. IFR training flights above 1,500 feet AGL at speeds in excess of 250 knots.
First time I've ever seen that question asked in the FAA exams. Next question is 231, bottom of the page. The vertical limits of that portion of the Federal Airway over Maggie Airport, north of Area C in Figure 16 are?
Well, remember when we were talking about VORs, we said that VOR, or Victor Airways, or the air routes, start at either 700 or 1,200 feet above the ground and then go up to, but not including, 18,000 feet, 17,999 feet. For the most part, that's true, but in mountainous terrain, you're going to have the airway actually starting at some higher elevation above the ground just because of the terrain. So what you need to know is that if the lines, just like in controlled or uncontrolled airspace, if the lines are magenta surrounding Victor air route, then that starts at 700 feet. The air route actually starts at 700 feet. If the lines are blue, it starts at 1,200 feet AGL, above ground level. And if it's blue and it has an extra number involved, in other words, it's labeled, then it starts at whatever that labeled number is. So let's find McGee Airport, and it's more or less in the center of chart 16 or figure 16. And we have the blue, but we also have a blue number showing 7,500 feet MSL. So the base of the airway starts at 7,500 feet and goes up to 17,990 feet. That's answer number 4.
Yeah, and even if you didn't know most of the information, just the second half of the answer gives it away with 17,999 feet because the Federal Airway System goes up to 18,000 feet MSL. Next question is 232. What is the upper limit of the Savannah Terminal Radar Service Area? See Figure 17.
Well, we'll turn to Figure 17 and find the Savannah Tersa, and the Tersa is shown by these magenta lines on Figure 17, that purplish brown color. And the upper limit is shown by some magenta numbers. There's a 55 and a line and a 100. That means that the base of the Tersa in this area is 5,500 feet, and the top of the Tersa is at 10,000 feet. If we go down just to the next area, we see that the base in this area is at 2,500 feet, and the top is also at 10,000 feet. Add 2 zeros. So the answer then to 232 is answer 3, 10,000 feet.
Question 233, the width of Victor 114, or Victor 114, we know Victor refers to a Federal Airway on Figure 18, from either side of the center line is?
Well, as we already discussed in regulations, I believe it was, any Victor air route is 4 degrees either side of the center line. I don't care if it's Victor 114 or Victor 263 or whatever. So without referring to the chart, we can answer this question. It's 4 nautical miles either side of center line, answer 2.
Question 234. Which cruising altitude is appropriate for a flight from Paris Vortac to Quitman Vortac on Figure 18?
Well, we have to find Paris Vortac and Quitman Vortac on Figure 18, and they're over on the right-hand side. Paris Vortac is this compass rose with a box showing Paris. That's how we can find Paris Vortac. If we go down by Area B, then we see another compass rose with a box showing Quitman Vortac. So that's probably on most of these problems, finding what they're talking about on the maps takes the most time for me anyway, of just trying to find what they're talking about. So the question is saying we're cruising from Paris Vortac to Quitman Vortac. Well, when we go from Paris to Quitman, we're going in a southeasterly direction. And if we're going southeasterly, then it would be odd altitudes plus 500. So you'd find an answer that has an odd altitude plus 500, and that's answer number 3, 5,500 feet.
Question 235. What minimum pilot certificate is required in order to fly from Area A to Area C in Figure 19 at 5,500 feet MSL?
Well, this is a rather confusing question because, first of all, by looking at Figure 19, we don't know if we're looking at a Group 1 TCA or a Group 2 TCA. We do know, though, that we're looking at a TCA because the blue lines shown here show us that this is a TCA. So we do know that this is a TCA. from area A to area C, you know you're within the TCA. They say that you're flying at 5,500 feet. Well, looking for blue numbers with a base and a top, we have surface to I don't know what that is, 7,000 feet in this area, and we have surface to 7,000 feet in this area, so you're within the TCA going from A to C. This LAX, Los Angeles, happens to be a Group 1 TCA, but that's really moot. We don't even need to know that, because anytime we're within a TCA, we are not required to have anything more than a student pilot's license unless we're landing at the primary field within that TCA in a Group 1 TCA. So the answer is number 1, student license.
Question 1236. What minimum radio equipment is required to operate in the airspace below 7,000 feet MSL and above 1,000 feet AGL over Los Angeles International Airport on Figure 19?
Okay, again, we just discussed how we would determine that we were in a TCA by the blue lines. And again, if you forget what a magenta line means or a blue line means, look back in the legend section and all that is in there. So we find that we're in a TCA. We don't know if we're in a Group 1 or Group 2 TCA, and I have a problem with answering this question. I happen to know that Los Angeles is a Group 1 TCA. I have spent 10 or 15 minutes looking at this chart to see if it says Group 1 or Group 2, and I cannot find that it says, but I'm telling you right now it's a Group 1 TCA. So if it's a Group 1 TCA, we need two-way radio communication. Just to operate within the TCA now I'm talking about, we need a transponder and we need mode C, or an altitude encoding transponder. So it's answer number 1, two-way radio communication equipment, a transponder, and encoding altimeter.
Question 1237. What minimum radio equipment is required for operation into Ontario International Airport on Figure 19, Area E?
Well, Figure 19, again, is our sectional showing the Los Angeles basin. Area E is to the east of Los Angeles, and Ontario Airport is actually this box with the two parallel runways shown here. But if we look just a little bit to the left, we see that it says Ontario ARSA. So that's actually an ARSA, and this dashed line, dashed circle shown around the Ontario Airport also would tell us that it's an ARSA. So that since we are within an ARSA, we know that we're required to have two-way radio communication. So it's answer number 4, two-way radio communications equipment.
Question number 238. The top of the ARSA at Ontario International Airport, Area E, is?
Remember, the ARSA, the top of the ARSA is 4,000 feet above ground level. So we just need to know that. We don't even have to refer to Figure 19 to answer that. So it's answer number 4, 4,000 feet above the airport.
Question 239. The base of the outer circle of the ARSA at Ontario International Airport is?
Again, we don't have to refer to the chart because we know just all ARSAs, the base, the inner circle is the surface. The top of the inner circle is 4,000 feet, and the base of the outer circle is 1,200 feet AGL, or above ground level, and the tops are 4,000 feet AGL. So it's answer number 4, 1,200 feet AGL.
Next question, 241. At which airport is fixed-wing special VFR not authorized in Figure 19?
Well, what we're looking for in Figure 19 is an area that is surrounded by a grouping or a line of T's. And what this line of T's tells us is that we have a control zone where special VFR is not authorized for fixed-wing aircraft. And again, if you don't know that or forget that, by the time you actually take the exam, go back into the legend and you'll find a line of T's and the description to the right of it. So we're looking for that. We would think it would be the most busiest or the busiest airport in the particular area, and that would be Los Angeles International. If we look over at Los Angeles International, which is near where Area A is, we'll see this circular band of T's that I'm talking about. And that tells us that we have a control zone where special VFR is not authorized. So that's answer number 2, Los Angeles International Airport.
Question 242. The airspace overlying Los Angeles International Airport is?
Again, we've talked about this. If you see those blue lines, that indicates that it's a TCA, Terminal Control Area. So it's answer number 1, a Terminal Control Area.
Question 243. The flag symbol at Lake Drummond, Area B in Figure 14 represents?
Figure 14 shows on the near arrow B this Lake Drummond and a little flag symbol. That flag symbol just means that it's a VFR checkpoint. In other words, you would report, that would be one of the areas over which you would report when you're entering Norfolk's airspace. So it's answer number 3, a visual checkpoint used to identify position for initial call-up to Norfolk Tersa.
Question 244, the word caution, Area A or Area E, denotes what hazard to aircraft?
Let's look at Area E. Area A is the same. We see the little letters caution, and they're really rather difficult to see. But notice also there's this line, which if we look in the legend, says that it's a power line that crosses the water and then goes back down to Kitty Hawk. That power line crossing the water is the caution they're talking about for low-flying airplanes or balloons or what have you. So the answer would be number 3, power lines crossing the body of water.
Question 245. The elevation of the Chesapeake Municipal Airport, Area B, is?
Well, again, looking at figure 14, near arrow B, or Area B, we find Chesapeake Municipal, which is this magenta area, and the box underneath has a 20 to the left of it. The elevation of the field is 20 feet. So the answer to the question, it's answer number 2, 20 feet.
Once again, there's another free answer if you want to look back in the legend on page 1 of Appendix 2. You could read that right off the sectional chart legend. Let's go on to question 247 on page 20. Which public use airports depicted in figure 15 are indicated as having fuel and a rotating beacon?
Well, again, if you don't know this, and you probably don't, you just look back in the legend and find out how we would find out whether or not a field has fuel and how we would find out whether or not a field has a beacon. A field has fuel if the circle depicting the runways has little notches or little ticks on it, like at north, south, east, and west. And a field has a beacon if it has an open star at the top of the airport diagram. So looking around, we find near on figure 15, near Area A, that Minot has these little ticks. There's one on the west, east, south. You really can't see one on the north. And Flying S Ranch has these little ticks on the west, south, and east. And it also has the open circle shown at the top of the airport diagram for both of them. So the answer would be Minot and Flying S Airport, which is answer number 1.
Question 248. Of what practical use, if any, are the private airports if a pilot does not have the owner's permission to use them?
Well, we could use them for navigation for dead reckoning if we're looking for a field at about our halfway point or something like that. And also, of course, for an emergency. If you have a problem, even if it's a closed airport, you'd rather put down there than in a forest or something. So it's answer number 4 as landmark value for navigation and emergency use.
Notice he said a closed airport, not a closed runway. Question 249, for information about the parachute jumping and glider operations at Henley Airport, Area B, refer to...
Well, I'm not going to refer to a chart because all you need to know here is that you would get information about glider operations, if there were any, and parachute jumping, if any, by referring to the Airport Facility Directory, or the AFD, and that's answer number 2, the Airport Facility Directory.
Question 251. What is the height of the lighted obstacle approximately 8 miles southwest of Savannah International, Area C, on figure 17?
Well, let's find Area C in figure 17, and that's down in the lower right-hand corner. As I said, probably the most difficult part of a lot of these problems is finding what they're talking about. We find Savannah Airport, and if you get your plotter out, you measure about 10 miles to the south west, we find a tower symbol, and again this is all in the legend, but this little pointed rocket shape is a tower symbol, and we have 2 numbers to the lower right of it, 1549 and 1532. 1549 tells us the height mean sea level, 1532 tells us the height in AGL, above the ground. So we're looking for an answer for either one of those, and it's answer number 2, 1532 AGL, above ground level.
Question 252, the military air station at El Toro, Area B, in figure 19, can be identified by a rotating beacon that emits, well, they already gave us the answer.
Sure. We don't even need to refer to the chart here. We've talked about this also in the AIM section. When you have two white flashes, that's a military field, so it's answer number 2, two quick white flashes between the green flashes.
Jeff, I don't believe that even looking at the chart would help us answer the question.
That's what I mean. Yeah, we don't even need to refer to it.
They're just sending you there for no reason at all.
Right.
Let's move on to question 258 at the bottom of the page. Determine the magnetic course from the first flight airport area E to Hampton Roads Airport area B in figure 14. I'd like to mention that you're going to need an E6B computer for this course, which is the classic navigation tool that's been used through the ages. What, 60 years of aviation, and it was previously called the Dalton Dead Reckoning computer, and now it's called an E6B. But go ahead, Jeff, why don't you take this question before we start with that?
Okay, we're going to figure 14, and we need to again find first flight airport area E and Hampton Roads area B. Well, first flight is down in the lower right-hand section, and all the way up at above B is our Hampton Roads. So that's what we're doing. We're going from first flight up to Hampton Roads, and I've drawn a red line here showing the course. That's what you're going to have to do. Again, you don't want to do it on the chart. You're going to have to do it on your plastic overlay that they give you for this exam. Now, before I even start figuring out mentally or mathematically this problem, I just look at it mentally and say, I'm going from down here to up here, so I'm going basically in a northwesterly direction. So the numbers I should come out with are going to be around, 300 degrees, 320 degrees, something in that area. If you come up with 090 or 120, you know that you're totally aiming in the wrong direction. So always have a broad, general idea of the answer, the range of the answer. So I'm looking for something around 300 degrees or 320 degrees. Once I draw my line, then I put my plotter on there, and I find a line of longitude. Once I find a line of longitude, I put my plotter on so that my hole on the plotter covers the point where the line that I've drawn intersects that line of longitude, and then I read off the heading right on that line of longitude at the top of the plotter. Now, if this seems, I know you can't see it so well on your television, you're really going to have to ask your instructor to help you out in doing these accurately. What I'm telling you is how to do it. You make a line, you find where that line intersects, a line of longitude or a line of latitude, you put the hole in the center of the plotter on that intersection of the line and the line of longitude preferably, or line of latitude if you don't have one, and then you read off the plotter what you're actually reading. And what you're reading is your true course. Your true, not magnetic. Remember that. It's true course. Then we, of course, would adjust true course for variation to come up with a magnetic course. And they ask here the magnetic course, so that's what we're going to have to do. So putting my plotter up against my line and the intersection, I come up with 321 degrees, which is about the ballpark that I was talking about. So I know that I came up with the right answer from that standpoint of being in the ballpark of the area. So 321 degrees. Now I need to find out the variation. Well, we look on the chart, someplace on this chart, there's got to be a dashed line with the variation listed. And way off to the right that passes through warning area W50, we see this magenta dashed line in a 9 degrees west. 9 degrees west is our variation. In other words, our magnetic North Pole is west of our true North Pole. So remembering the mnemonic, east is least and west is best, we would add a westerly variation or subtract a easterly variation. This is west, so we add 9 degrees to 321 degrees, comes up with 330 degrees, and that's answer number 3. Notice that one of the choices is 321 degrees, so they're ready to grab you if you forget to take into account your variation.
Yeah, and I'd like to mention right along those lines that whenever we talk about a true course or a true anything on a chart, we're just talking about the line on the chart, which isn't of much value to us except to come up with something magnetic, which is subtracting for variation. So when you hear the word true, you're just thinking of a line on a chart. When you hear the word magnetic, you're thinking of something you would do in the airplane. Question 259. En route to First Flight Airport, Area E, your flight passes over Hampton Roads Airport, Area B, at 14:56, and then over Chesapeake Municipal at 15:01. At what time should you arrive at first flight?
Okay, this question is really a reverse of the previous one. In the first one, we were going from first flight up to Hampton Roads, and now we're on a flight, and we go over Hampton Roads on our way towards first flight. So we can use that same line that we drew. So what you need to do is, after you find first Hampton Roads and Chesapeake Muni, you need to measure the distance between those two. And again, you would use your sectional plotter and just measure the distance off. Be sure that one side says sectional and one side says our WAC scale. So be sure you're on the sectional scale, and if you forget if this is a sectional or a WAC, it'll say at the top of the chart that it is a sectional. So be sure you're on the right scale. Measuring the distance between Hampton Roads and Chesapeake Muni, I come up with 10 miles. Well, they look at the times that it took for you to go from Hampton Roads to Chesapeake Muni, 1456 to 1501. That's 5 minutes. So to go 10 miles, it took you 5 minutes. So now you need to measure how far is it from Chesapeake Muni then down to first flight. And again, you'd get your plotter out and just measure that distance, and that's something just under 50 nautical miles, around 49.5 nautical miles. So we have a mathematical relationship. If you wanted to do it that way, it takes you 5 minutes to go 10 miles. How many minutes will it take you to go 50 miles? You can do it that way, or you can pull out your trusty E6B, and just like on the computer side here, we'd put the minutes on the inside scale, 5 minutes, and match it against miles on the outside scale, 10 miles. And when you do that, you come up with, and then find for 49.5 miles, and you come up with 25 minutes. It would take you 25 minutes to go 50 miles if it takes you 5 minutes to go 10 miles. So you add 25 minutes to the time you crossed Chesapeake Municipal, which is 1501. The 1526 would be expected arrival time at First Flight Airport, and that's answer number 3.
You can just kind of figure those out in your head.
Well, that one you can. It's a pretty easy mathematical relationship. Sometimes, and I'll show you how to do it on this and another one, sometimes you just have to go to the E6B. There's no way you could do it. Well, there's no way a normal person could do it.
And another nice thing I know when you show us the E6B is all the information on how to use it. It's right on the face of the instrument.
Right. You don't have to memorize a lot of it. It's all right there.
Good. Question 260. Determine the magnetic heading for a flight from Hazen Airport Area C to Minot International Area A. The wind is from 330 at 25 and the true airspeed is 100. I'd like to mention again, I mentioned that a true course is a line on a chart, a magnetic course is corrected for variation. Whenever we hear the word heading, we're correcting for wind. So it's true course plus or minus variation equals magnetic course, plus or minus our wind makes it magnetic heading, plus or minus our compass deviation will give us our compass course.
Right. Okay, we need to, first of all, again, question 260, we need to find out, where we are and then draw the line and whatnot. On figure 15 now, we're going from Hazen Airport, Area C, which is down here in the lower left-hand corner, up to Minot near Area A. So we're going basically a northerly heading, and it looks east of north. So I'm going to be looking for something around, 020, 010, something like that would be the basic ballpark. If I get 180, I'll know that I'm finding something that's 180 degrees out or in the wrong direction. Anyway, so once I find my two spots, I draw a line, and again, you're going to have to do it on the plastic overlay, and I take my plotter and find where this line intersects a line of longitude or latitude, and then plot it using the plotter. And when I do that, I come up with 012, or 12 degrees. 012 is my true course. And that's my true course before, as Steve said, I take into account variation, or before I take into account the wind. So let's correct for wind. Let's look at the wind side of the computer, and notice at the top of the sliding scale here, we have directions on any E6B or any computer that you're going to use. You're going to have directions on the computer itself. Also, you're going to have a booklet that gives you instructions that comes with it. So become familiar with this computer before you walk in to take the exam. But we're just going to follow these steps, and I'm showing you exactly how we're going to do that. The first step is to move the true wind. They give us that the wind is from 330 degrees at 25 knots. So I move the wind under the true index. Once I do that, I move the sliding scale to position the grommet over one of these major lines so that I can count up 25 knots. because they give us that the winds are 25 knots. There's 10, 20, 25, and I've already drawn a dot with a circle to catch our attention. So that's the wind. Then the next step is to rotate the scale with the wind dot on it until we read the true course that we determined from the chart. We determined that it was 012 for the true course, so we put 012 under the true index. Once we have 012, now we see that the dot has gone off to the left. Now that tells us that our wind correction angle is to the left, and we can just think about this and determine that. We're going basically north. The wind is from 330 degrees or out of the northwest, so the wind is from, it's a left quartering headwind, so our nose is going to have to be a little bit to the left to maintain our track into the particular airport. So just knowing that, that tells us that our wind correction angle is to the left and not to the right. Back to the computer now, E6B, we would move our sliding scale until the wind dot that we drew is over the line for our true airspeed. Now we're given that that's 100 knots. So here's 100 knots, this curved line. We just move it so that we have 100 knots underneath that line. Once we do that, we can read two things. We can read our ground speed underneath the grommet. That's right at 80 knots. We'll use that actually for the next problem. But we can also read the actual wind correction angle. We knew it was to the left, but now we can determine how much to the left. And you see these lines that go up and down. Those are our wind correction angles. And the dot is right over the 10-degree line. So once we have that, that's about our third step in this problem. We have a 10-degree left wind correction angle. Well, if it's left, in other words, we were heading 012 and it's 10 degrees west to the left, we would actually move the nose 10 degrees to the left or subtract 10 degrees from 012, giving us 002, and that would be our true heading, because that's our heading, it's our true course modified for the actual winds. Well, there's one more step. Because they're asking for magnetic heading, not true heading, we need to go back to figure 15 and find the variation on the chart. We find our magenta dashed line here showing us the variation, and it's 11 degrees east. East is least, west is best. East is least, we subtract 11 degrees from our true heading, which was 002, and when you do that, it's 351 degrees, because 000 is the same as 360. So our answer is 351 degrees, and that's answer number 1.
261, next question. What is the estimated time en route from Hazen Airport, Area C, to Minot International, Area A? The wind is from 330 at 25, and the true airspeed is 100 knots. Add 3.5 minutes for departure and climb out.
Now we use the opposite side of the E6B, what I call the slide rule side, and that's just like it's a circular slide rule is all it is. And what we do here is find the big dark triangle and put that underneath the true airspeed. And if you forget that if the true airspeed is supposed to be on the inside scale, on the outside scale, you can just look around the scale and it'll tell you. And somewhere on this outside scale it's going to say true airspeed, and it does, right near the 8. See TAS, true airspeed. So you know true airspeed is on the outside scale. Time, because this dot or this triangle means an hour or a minute or whatever, time is on the inside scale. So once we have 80 knots set over our speed index, that big triangle, now we find for our distance, and distance would be on our outside scale, and we would read time on our inside scale. We would measure distance off the chart using our plotter. When we do that, we come up with 59 nautical miles, and that's the distance between Hazen Airport and Minot International, 59 miles. So then we go back to our computer side of the E6B, find 59 on the outside scale, and we'll read minutes on the inside scale. And when you read 59, here I'll just point it out. Here's 55, here's 60, so that's 56, 57, 58, 59, and that would be 59 and a half. So there's 59. We read down to find the time. There's 40 minutes, 41, 42, 43, 44. There's 45, right at 44 and a half minutes. So that's what we come up with, 44 and a half minutes. is the time to go 59 miles when we're traveling at 80 knots. Now there's one more part of this problem, and that says add 3.5 minutes for departure and climb out. So we add 3.5 to 44.5 and come up with 48 minutes. And that's answer number 2.
If you forgot to add the 3.5, they have an answer
There's an
waiting
answer
for you.
Right.
Answer number 1. Let's move on to question 268. Determine the compass heading for a flight from Allendale County Airport at Area A to Claxton Evans County Airport, Area B. The wind is from 090 at 16, and the true airspeed is 90 knots.
Okay, let's look at figure 17 in this section. Allendale is at the top of the figure, and Claxton is way over here in the lower left-hand corner. So we're going from this airport down to this airport. We're going to the southwest. Again, we're going to be looking for something around 220 degrees maybe, 230 degrees, something in that area. And I always get that in my mind first before I start figuring out actual numbers, because I'll very easily misread my plotter if I don't have a hint on what I'm looking for if I don't do that. So once I do that, again, we use our plotter, find where the line crosses a line of longitude, put the point of the plotter right over that intersection, and you're not going to be able to see it on television, but when you actually do this, you can do it at home and mark up your charts to your heart's delight. You're not going to be able to do it on the actual test. So I would suggest you go through, especially in this navigational section, go through each one of these problems and make sure you can come out with the answer that we've given you because they are the correct answers. So once we do that, we come up with a true course of 213 degrees for that course from Allendale to Claxton Evans. Next, we have to correct for wind. We'll turn to the wind side of our computer again, move underneath the true index. We want to move 090 because the winds were given as 090 at
16 knots.
16 knots, thank you. So we first of all move our grommet up to a line and measure 60. Once we have 090 under the true index, measure 16 knots, which would be right about there. Little dot with a circle, so that'll catch our attention. And next we move underneath the true index, we move our true course of 213 degrees. Now 213 degrees would be right about there. We notice that our dot is below our grommet. In other words, now we're going to have a left quartering tailwind for this particular flight, which would agree, just thinking about it, you're heading about 213 degrees and the wind is from 090, or in other words, you're heading to the southwest and the wind is from the east. You're going to have a left quartering tailwind. It's going to be over your left shoulder. So that agrees, just again thinking about the situation. So once we do that, we put back to the wind side of the computer, we put that dot, the wind dot, over the true airspeed, which was given as 90 knots. So we move the dot over our 90 knot line, which is on the sliding scale, and we can read two things. We can read underneath the grommet, we can read the ground speed, and underneath the dot from these lines we can read our actual wind correction angle. Our wind correction angle is 9 degrees left, and our ground speed is 97 knots. So again, we're just following the steps. If you're confused as to where we are, we're following the steps found on the E6B. We're changing our true course. We're correcting for wind. Then we're correct for variation to get our magnetic heading. And then they ask for compass heading. So then we're going to have to correct that for deviation. And I'll show you where we find deviation in just a moment. So we had 213 degrees as our true course. Wind correction angle was 9 degrees left. So we subtract 9 degrees from 213, giving us 204 degrees, and that would be our true heading. Next, we need to correct for variation. So we look somewhere on the chart to find our variation dotted magenta line, and that's found over here, and we can see that it's 3 degrees west. East is least, west is best. Add west, so we would add 3 degrees. Add 3 to 204 degrees, and that's 207 degrees. That's our magnetic heading. That's not our compass heading, which is what they asked for, and I imagine they'd probably have an answer pretty close to that. But we need to find now our deviation. Now to find our deviation, we look for some sort of a deviation compass card, and they just have an excerpt. Well, you actually would not, of course, find that on the chart. I say, of course, but in case you don't know it, you would not find this on the chart. You would find this on your airplane. It depends on the particular airplane, and it would be located probably around the magnetic compass. And that they swing these compasses. That's what they talk about, swinging these compasses. And they say in order to fly north, you would actually steer on the magnetic compass 0 degrees or north. There's no deviation if you're heading north. In order to fly 030 degrees, you would actually fly 027 degrees. So there's -3 degrees deviation if you want to fly to 030. We want to fly, though, 210. We're in the vicinity of 210, and that's right below that. Where it says 210 degrees, you would actually fly, according to our deviation card, 214. So it's +4 degrees. So we had 200